All right, everybody, this is our last video for this week, and we'll be going through different techniques for computing limits algebraically. Okay, so first one, sometimes we'll have the case where we're looking for the limit as x approaches some number, in this case is 3, and then we've got a function and we can just plug the 3 in. So we can just plug the 3 in and then simplify it down and we get 11 over 2. Okay, so that's kind of our first technique, is if we can plug it in, we do that. Okay. Sometimes we'll have a constant. So here we're looking at the limit as x approaches 2, but there is no x in our function. Our function is just 6. So that means this limit is going to be equal to 6. So the limit of a constant is that constant. Okay. If you've got something like the limit as x approaches 3 of 6h, okay, where we do have a variable in there, but none of the variables that we're looking for with the limit. Okay, so in this case, it would still just be 6h because the variables are different. Okay. So those are kind of our two base techniques for computing limits. We've got several, we call them the limit laws, and therefore when we've got like a combination of limits or some other operations dealing with limits, okay, so you would use the combination of these and the ones above to solve different ones. So if you've got the limit as x approaches a and the limit of as g approach, the limit is x approaches a of g of x. So we've got our limits of two different functions and we're approaching the same number, which is important. And so since they exist, then we can do all of these properties. So the limit of two functions is the same as the limit as x approaches a of the first function plus the limit as x approaches a of the second function. Okay, so if you've got the sum of two functions, they can be split, and all of these work backwards too. I don't know how often they'd be used backwards, but, and then we've got difference, and this should just be a minus. So if we've got the limit as x approaches a of f of x minus g of x, okay, just like with the sum, we can split it. So we've got the limit as x approaches a of f of x minus the limit as x approaches a of g of x. Okay. If we've got a constant multiple, so c is just some constant number, we can pull that out to the front of the limit. So that's the same as c times the limit as x approaches a of f of x. If we've got a product of two limits, we can separate those, and so it would be we could do the limit as x approaches a of f of x times the limit as x approaches a of g of x. Okay, similar with the quotient, we could do would be the limit as x approaches a of f of x divided by the limit as x approaches a of g of x. Okay, so we've got the sum and the difference and the product and the quotient. We're just kind of distributing the limit in a sense. Okay, and then you've got the constant multiple where you're popping that out. And our last two are the same rule, really, just dealing with powers and roots. And so if you've got the limit of some function to a power, we can pull the power out and do that outside of the limit. So for this one, it would be the limit as x approaches a of f of x to whatever that power is. And then the root would be the same way. And then remembering that also could be the nth root of the limit as x approaches a of f of x. Okay. So when you're solving or computing limits, you'll use a combination of these things. Just depends on the problem itself. So the limit laws will be really useful if you've got problems like this example where we're given, we don't know what our functions are, but we're given their limits. So we can use our laws up above to get it down to where we're taking the limits of the individual functions because we know how to do those. Okay, so for example, we've got the quotient property, so we'll have the limit as x approaches 2 f of x minus g of x divided by the limit as x approaches 2 of h of x. And then we can split that over the difference. So the limit as x approaches 2 of f of x minus the limit as x approaches 2 of g of x over the limit as x approaches 2 of h of x. And so now that we've got this down to the individual limits, so we've got the limit as x approaches 2 of f of x, we've got the limit of g of x and the limit of h of x, we know what these values are and can substitute them in. Okay, we couldn't do that before because we didn't know the values for f of x, g of x, and h of x. We just know the values of their limits. So we have to simplify it to that point before we can use them. Okay, so we plug those values in and we get 4 minus 5 divided by 8, which will be negative 1/8. Okay, sometimes we'll have the case where we look at it and we have the function, so we want to take the limit of this function. So it's the limit as x approaches negative 6 of x plus 6 over x squared minus 36. If I were to try to just plug negative 6 in, I would get something of the form 0 over 0. So we can't just plug in 6 because, or negative 6, because then we would get 0 over 0 form, which we can't have because you can't divide by 0. So that's when we try to cancel something. So we try to factor to cancel something. Generally, whatever is causing it to be 0 over 0. So we'll factor the denominator. So we get the limit as x approaches negative 6, x plus 6 over x plus 6, x minus 6. Okay, so we can cancel the x plus 6's, and we're left with the limit as x approaches negative 6 of 1 over x minus 6, which we can plug that in. So it's 1 over negative 6 minus 6, which is negative 1/12. Okay, so if you can't immediately plug something in, you might have to do a little manipulation in order to be able to plug it in. And one way you'll do that is factoring, and there's another way we'll do that in just a few examples. But first we'll do this example. So let's say we've got this. When you've got any limit where it's a fraction and you've got variables in the denominator, you've got to make sure that your 2 is not going to cause a 0, or your whatever it is that you're plugging in is not going to cause that denominator to be 0. And because of our denominator, we don't have to worry about that. So we can go ahead and plug it in. So we get square root of 2 times 2 cubed plus 9 plus 3 times 2 minus 1 over 4 times 2 plus 1. So another thing with notation. So before, up here, we kept writing the limit. We had equals to limit, equals to limit, equals to limit. You continue to do that up until when you plug it in. So that step where you plug it in, you no longer write the limit. So we wrote them out there. This one, we could plug it in immediately, so we don't write that limit outside of that first step. Okay, but we still have to make sure we include our equals going down. So we simplify and we get the square root of 25 plus 6 minus 1 divided by 8 plus 1. So 5 plus 6 minus 1 over 9. So 10 over 9. Okay. So that one looked scarier than it was. All right, and then we'll do another example. So with a square root like this, we know that we can't have a negative under the square root. So do a little side note over here. So we know that 16 minus x to the 4th has to be greater than or equal to 0. Okay. So then we get 16 has to be greater than or equal to x to the 4th. That's a typo. Okay, this should be a 2 up here. Okay, that should be a 2. So then we've got 2's here. Okay. All right, so then we get that x, we have positive or negative x is less than or equal to 4. Okay, so we split these. So this, we've got 4 is greater than or equal to positive x, and 4 is greater than or equal to negative x. Okay, so this means that x, negative 4, is less than or equal to positive x. So we divide by the negative and flip the sign, okay, to get our x value. So we know that x has to be is only defined inside of this range, okay? And so since we've got a square root, we'll take the left and the right hand limits of this point. And remember, if we take both the right and the left hand limit, then we get that it's equal. Or if those are equal, then we have that limit. But if we look, we go to take our left and right hand limits. So we'll do the left hand one first. And so we see that, oh, well, the limit as x approaches negative 4 from the left of 16 minus x squared does not exist, okay? And it does not exist because negative x is not defined for values less than 4 or negative 4. Okay, x is only defined to be greater than negative 4, but it's not defined to be less than negative 4. Okay, so that left-handed side limit doesn't exist. So that means that our limit as x approaches negative 4 of 6 square root of 16 minus x squared does not exist. Okay. So sometimes if you've got something like that, a radical like that, you'll need to check both sides as opposed to just plugging it in. And then we'll do this example. So this example, I can't plug it in because that would again give me 0 over 0. So, and I can't factor anything. So then our next step is to try a conjugate. Okay, so if we multiply this, so we've got the limit as x approaches 1 of square root of x minus 1 over x minus 1, and we multiply by a conjugate, so we've got x, square root of x plus 1 over square root of x plus 1. So we get the limit as x approaches 1 of x minus 1 over x minus 1 times root x plus 1. These cancel. So we're left with the limit of x as x approaches 1 of 1 over root x plus 1. And now I can plug it in. So it's just 1 over root 1 plus 1, so 1/2. Okay. So you'll try to plug it in if you can. If you can't, because it's 0 over 0 form, then try factoring or conjugate, depending on what the equation itself looks like. Okay. And then our last thing we're going to talk about is squeeze theorem. So sometimes we can't necessarily find the limit of the function we're given, but if we know that the function is between two other functions that we do know the limit of, then it has to go, or it has to be equal to the same thing. So if we've got three functions, f of x less than or equal to g of x less than or equal to h of x, we've got three functions and one is in the middle. Okay, if we know the limit of the two outside functions equal the same thing, then whatever's in the middle has to be equal to that too. Okay, so if we look at f of x is equal to x squared sine of 1 over x, okay, and we want to take the limit as x approaches 0 of that, but I can't do that because I can't plug it in, because that would give me 1 over 0 on the inside, and because that's in a sine function, I can't factor, I can't do a conjugate. So what we do instead is we know that sine is in between -1 and 1. So we know the sine of 1 over x is in between -1 and 1. Okay, I can multiply, I need this x squared, so I can multiply everything by x squared. So we get, our arrow there just means implied. So we get negative x squared is less than or equal to x squared sine 1 over x is less than or equal to x squared. Okay, so now we've got our function in between two things that we know how to take a limit of. Okay, so this means if we take the limit of each of these as x approaches 0, okay, we can plug in our 0 values for over here, and so we get that this limit is equal to 0, this limit is equal to 0, and the limit x approaches 0 of x squared sine of x is in between these two, or sine of 1 over x. So because it's got to be greater than or equal to 0 and less than or equal to 0, then it has to be equal to 0 as well. Okay, so by the squeeze theorem, that's what we call that. The limit as x approaches 0 of x squared sine of 1 over x is equal to 0. Okay, we call it the squeeze theorem because it's like, do you know what the two outside ones are? So if you're squeezing, whatever's in between there also has to equal 0. Okay, or whatever that same value is. It won't necessarily be 0. Okay, these are some of the common techniques we'll use for limits. And so we'll do a bunch of examples with these in practice Wednesday and Thursday this week.